this video will highlight how the group saved the world using the boost, LabVIEW, and the cooling system, and also explain the differences in performance.
Hi, Boost Boy here. Moving on to the system boost converter design. This was a key step in the development of the solar phone charger, as a lot of analysis of each circuit component was required to optimize the performance of the boost converter in 3 ways. Number 1, to maximize the system power output, reducing total power losses in each component. Number 2, make the output power consistent by reducing the amplitude of the output power signal. And number 3, make the output power selection as accurate as possible. The majority of the boost converter design was conducted using parametric analyses on LT-Spice, while referencing our physical circuit to make sure we observed the same results. LT-Spice was a highly useful tool for doing collaborative work remotely, as we were able to easily share simulations to get each other's opinions on them, as well as to use simulations as circuit schematics to make sure we all had the same setup. In terms of the boost converter's capabilities, our final design recorded a top efficiency of 86% when operating at max output power, with the amplitude of the system output power signal being reduced to approximately 1.5% according to LT-Spice simulations. Finally, we could select the output power within a margin of approximately 1 to 3 milliwatts.
For the SOLA2051 project, we also had to create a LabVIEW VI that outputs values to the cloud. To do so, we implemented what we learned in labs, as well as PID integration and inputting a time delay. A backup data storage was also created in the event of potential upload failure. Even though we each individually calibrated our current sense amplifiers, on the day of the test we forgot to input our values into the LabVIEW and use values for a current sense amplifier that none of us were even using. This resulted in an incorrect large value for power in, which affected the actual performance of the system.
We all love hot things. Hot food on a cold winter's day, hot people to admire, but a hot solar panel, not so much. In a society where coal has run out and we're relying on this solar panel for electricity, we also have to design a system that will keep the panel cool during its operation. During such difficult times, we have to design and build this system out of recycled materials and make full use of their properties. The system that we have come up with utilizes convection and conduction in order to transfer and dissipate heat away from the panel during its operation, allowing it to perform optimally throughout the whole hour of operation and when you need it the most during the apocalypse. We constructed the platform out of light-colored cardboard as it is mechanically strong enough to hold the panel and has poor heat absorption and conductivity properties. This means that the heat from the cardboard won't be transferred into the panel, thus won't ruin its efficiency. The cardboard is from an old cereal box, rescued from the recycling bin and given new life in our project. We fastened aluminium to the back of the panel to conduct heat via these long tendrils into a big jug of water. Since water has a really high heat capacity, it can absorb a lot of thermal energy without heating up. All of the components were fastened together with generous amounts of sticky tape and glue. Our apparatus has an open design, allowing wind to flow all around the panel and through the aluminium tendrils. This further aids in cooling as heat from the panel itself and in the foil can be transferred to the wind and dispersed into the atmosphere, further aiding in keeping the panel cool.
I'll now run you through some of the differences we observed between our system's performance on the day compared to the results we predicted. While performing some preemptive testing on the day, we noticed an issue with our LabVIEW PID that we couldn't resolve, so we defaulted to using the trim pot to change the system's duty cycle. Unfortunately, using the trim pot meant we had to manually adjust the duty cycle depending on the panel's varying performance, making it more difficult to maintain our power output within 5% of the required value. On the day, our primary difference in performance was one system only reaching a max output power of 300 milliwatts, less than half of the other 2 systems. Some post-test analysis revealed that the circuit's trim pot had started malfunctioning and could only vary the pin 2, pin 3 resistance between 65 and 100 kiloohms. This subsequently limited the duty cycle between 58 and 100%, making the system unable to reach max power output. Our other 2 systems performed well, but reported a 10% lower output power than what we would have predicted for those levels of irradiance. Inspecting our circuit, we found this was primarily due to the lack of considerations of the resistances in the rigid jumper cables in series with the inductor. Each only had a series resistance of about 0.15 ohms, but together that would have led to a 5 to 7% power loss.